Thanks a lot, Professor Yang, for this kind introduction, and also very much thank you for this kind invitation. So first, to double check, can you hear me well and also see my presentation? I already share my slides.
Yeah, very clear, and your slides is very clear also. Yeah.
Good, good. I have a request to the audience because I hear noise, and please, if you can unmute yourself, that would be very much appreciated. Yes, okay, I will start. Good morning, good afternoon, and good evening. I understand there's many participants from all over the world, so very, very happy to be here to give this talk and to share our recent work on numerical modeling of reacting flows. I know that my title is quite long, but what I really want to highlight in this presentation is a few keywords. That is coarse graining and reacting flows and polydisperse particles. And you will see it's coming in my presentation coming. And of course, this is not my work alone. So this actually is done by an excellent team, where I have the name listed here. Wait a second, let me go to the laser point. Yeah, so let's start. This is the outline of my talk in the coming half hour or so. So I will start with a very brief motivation and followed by introduction of numerical methods. And mainly it's about some development in the framework of CFD-DEM. And after that, I will, if time allows, I will show you 3 examples where the developed numerical framework has been applied to understand the flow phenomenon in different type of reactors. Well, I don't think it's very necessary to motivate this community about the modeling of multiphase flow, but then anyhow, I will give a few highlights. And so, as you know, that these multiphase flows are encountered in many industrial applications. In this talk, I will talk about 2 examples. One is fluidized bed, which we have heard a lot from the previous talk from David again. So that's thanks, David. And then I don't need to talk further about fluidized bed. And the second example application is about blast furnace, which is a conventional reactor for making iron in steel making industries. And the multiphase flows encountered in such kind of applications usually is intrinsically multi-scale, meaning that the scale range from the particle size usually is about millimeter or even micrometers up to the reactor size. As you can see here, the reactor size can be up to in the order of meters. And sometimes, and in quite often situations, there are complex chemical reactions involved. And in terms of particle size, usually it's not homogeneous, so meaning that the particle size is dispersed, and also the shape of the particle are not very spherical usually. So each of these characteristics actually posed challenges to numerical modeling of these flow problems. And in the coming method introduction, I will talk about how to deal with those challenges. And first, to tackle the challenge of multi-scale feature, and of course, we cannot model the entire reactor in one single model. So usually a multi-scale modeling framework it can be used. David also shared a quite complete framework here. I show it only with 3 types of modeling, from direct numerical simulation to discrete elements method and up to 2-fluid model. And from left to right, you can see that you can simulate larger geometry in terms of larger scale, but however, the details which you can resolve is lost. So that's why usually the closure models are required, and which can actually be developed from the lower scale simulations. And thanks to the advancement in numerical algorithm and also the computing power recently, At the intermediate scale of the discrete elements method has become a popular framework. This is also the framework we will use, and is also the focus of my presentation today. And how does it work? In this model, it involves the CFD grade, which is used to solve the Navier-Stokes equations of the gas phase. And so it can, in that sense, we can keep track of gas velocity, pressure, temperature, etc. And each particles is checked individually in a Lagrangian fashion, meaning that the motion of particles is solved, and to update the velocity position of the particles every time step. And of course, the two phases need to be coupled, and usually the coupling is via the information change, which involves particle velocity, for instance, particle volume fraction, and also the momentum, mass, and heat transfer. And very commonly, a drag closure is used for the momentum transfer, and also etc. Mass and heat transfer coefficient closure also need to be used. A basic requirement for such kind of modeling method is that the size of the CFD grade needs to be larger than particle size in order to be correctly determine the solid volume fractions. That is essentially very important to properly capture the mesoscale structure. And we have a rule of thumb is that usually the grid size is about 3 to 4 times the particle size. As I said before, that the discrete element simulations track individual particles. So if we're gonna simulate large scales with, for instance, in pilot scale of reactor or even industry scale reactor, there are too many particles involved. So it's easily to be millions or billions of particles, or even more. And in this case, tracking particles individually, we are both challenges, numerical challenges for the simulation. So the model reduction here, the aim is to simulate fewer particles, but however, in the meanwhile, try to maintain the accuracy. This is a so-called coarse-graining approach. The essence of this approach is actually to represent a group of particles, of small particles, by a larger parcel. We call it a parcel. Sometimes you can call it in just other numerical particles. And in this case, if I give example, for instance, an original system, if it contains, let's say, 1 million of particles with a size of 100 micrometer, and if we scale the particle size by a factor of 2, and then the parcel size will be 200 micron. However, the number of particles in total we simulate in the simulation will be reduced 8 times. That means you only need to simulate 125,000 particles. Computationally, this is much cheaper. The question is how to maintain the original physics. And there are different types of coarse-graining approach. And in our case, we follow the collision-based scaling rules. Essentially, it means that the energy loss per collision between partials needs to be identical to the energy lost from the primary particle collisions. And practically, we need to scale the collision coefficient. For instance, the normal stiffness need to be scaled linearly with this coarse-graining factor, which is the ratio between the size of the particle and the size of the primary particle. And the damping coefficient need to be scaled with this alpha square. That's how it works for the collision. Of course, we also have to scale the other forces, for instance, drag force. And if we have mass transfer, heat transfer involved, we need to scale up properly as well. But I will not go that into detail in this slide. After coarse-graining, we can easily end up the situation like I put here. That is the size of the CFD grade is is comparable to the size of the particle or the particle size. This is, of course, conflict with the basic resolution rules I just talked about for the DEM simulations. And how, in this case, what we need to do is essentially to mapping or redistribution the information of the particles from the location of the particle to the surrounding CFD grid. This is how it visually look like. And this can be done simply by solving a diffusion equation of this transferring property phi. So this property, this phi is a general factor, which can be, for instance, the solid volume fraction, can be the Jack coefficient, like heat transfer coefficient, etc. And here the diffusivity is the only thing we need to do that. This diffusivity usually is determined by characteristic length L and the time scale. So this L, we usually correlate it to the particle size, and it's also for dense gas solid system, it's also about around 3 times particle size. The problem raises when we encounter polydisperse particles. And with the conventional diffusion-based smoothing scheme, which I just talked about it, and this constant length scale is used to determine the diffusivity. In that case, this results to an identical smoothing area of each particles. So that means no matter of the particle size, the inference area of the particle is the same. That means even the smallest particle can influence the surrounding fluid in the same way as the largest particles. This is, of course, not realistic. Instead, we would like to have the situation look like the right figure. In that sense, the inference area of the particle should be dependent on the size of the particle itself. So meaning the larger the particle, the larger the inference area, the smaller the inference area. And theoretically, this can be done actually quite easy by replacing this constant diffusivity with a diffusivity depending on the local particle mean diameter. This D is 32 is this mean diameter of the particle in the local cell. And however, when we try to implement in the solver, it is not very straightforward. I will not give the details. I will leave it here for now, and I will refer to our publications in chemical engineering science. And this publication, you can find more details about the implementation of this so-called particle size dependent smoothing scheme, and how to first, for instance, how to first smoothing the diameter, then be able to determine the diffusivity, etc. As for reacting flows, there's also possibility to have a model reduction as well. This can be done via a so-called flamelet generated manifold method. This method has been commonly used for gas combustion, where there are many reactions and chemical species are involved. And usually in such kind of combustion, you have dozens of species and hundreds of reactions. So you can imagine if you want to resolve all the species and reactions in detailed chemistry simulations, this will be way too expensive. What we can do is to actually pre-calculate a collection of this type of 1D flamelet and store the data in a database for a lookup table. And this database actually store all the possibility of combustion state and then the thermochemical property like concentration, density, viscosity, temperature, etc. are all stored in this lookup table. And this database way then incorporate in the CFD simulation. That's during the simulation, we only need to solve 1 or 2 scalar equations, and to track the state of the combustion. And with that, we can look up from the table for all the information we needed. If we have done the test for a very simple methane flame, so the left side is the temperature profile of resulted from detailed chemistry simulation. The right side is from the FGM simulation result. And you can barely see any difference. So basically the results are identical. However, the simulation with the FGM simulation is 100 times faster. So this really saves a lot of computational power. I think this is the end of the numerical method, and I will continue with examples where we have used this established numerical framework to model different type of flow problems. The first one is actually so-called pulverized coal jet flame. This is an experiment done by Huang et al. In 2007. This is a very standard experiment case where it has been used as a numerical validation in open literature. So we also did the same test using our numeric framework. And this is the geometry for the computation simulation. And a cylindrical domain is constructed for the simulation, and with the nozzle is located in the center of the domain. And this is how the mesh looks like. We have applied the mesh refinement in the central line where mostly the flame will be located. The pulverized coal particles is carried by the air, and it was injected from the center of the nozzle. And in the outer ring there is a methane air. Methane is injected to actually stabilizing the flame. And surrounding this outer ring, there's also a cold flow air. And the particle size, the particle size, of course, is polydisperse. It ranges from around 10 micron to 60 micron. And this movie has shown the trajectory of the coal particles, and the particles are colored by the temperature. This snapshot is also from this. The result is the flame. It shows the coal flame. As you can see, that there's a high temperature region and be formed by due to the combustion. Actually, in the center of the flame, there is a low temperature area that is basically due to the presence of the cold particles. And at the downstream, there is let's say the inward of the hot gas, or the hot gas temperature goes inward, and also due to the turbulent fluctuation. So there's the higher the temperature increase in the central line. And if we can plot along the center line the oxygen concentration. So this is the oxygen molar fraction as a function of the distance x from the starting of the nozzle, and the dashed line is the simulation result, and the symbols are the experiment data. As you can see, that the simulation can capture the general trend of the experiment data, meaning that the oxygen level is decreasing along the central line because the oxygen is consumed by the coal combustion. And however, when no smoothing scheme is used, like I said, due to the coarse-graining, and the particle size is comparable to the CFD grid size, but if we don't use any smoothing scheme, then you can clearly see the discrepancy between the simulation result and experiment result. And if we analyze our result, why does this happen? And this is actually a snapshot of this fuel release, meaning that the devolatilization rate of the core particles, and this is the control of the release rate. And if we zoom in, then you can see this pointy pattern, which indicates concentrated fuel release. So meaning that if this particle at this grid cells, all the fuel released by this particle is only concentrated at this cell. And due to this high concentration of fuel, then it also consumes more oxygen. That's why we have a lower oxygen fraction than the experimental data. If we apply the smoothing scheme, but with this constant length scale, and you can see that the result has been improved very, very, very much. However, we can obtain an almost excellent agreement if we have corrected this length scale with the local particle size. And again, we can also look at the result of this fuel release distribution after applying this particle size dependent smoothing scheme. So you can clearly see that those pointy place are disappeared. They become much smoothed. So this indicates the fuel released by the particles is distributed or is spreading nearby the surrounding cells. So this is exactly what should happen. And for more details, again, I refer to our publication and in this in CES again, and you can find more validation of our numerical framework. The second example I would like to move on is I already briefly had the introduction, is about blast furnace. This is a picture of a real blast furnace at Tata Steel in IJmuiden in the Netherlands. How it works is actually the iron ore and the coke, they are charged from the top into the furnace layer by layer, and the gasification of the core provide the heat and reducing gas for reduction of the iron ore into iron. And as you can see, this furnace is huge, so it is actually a mission impossible to simulate it in a single model. So that's why our project target at the lower part, where is nearby this injection zone. And here is a zoom in picture of this injection area. So the hot air is blasted into the coke bed together with injection of pulverized coal, and this due to the blast gas, and creates a void which is called raceway. So the formation of and evolution of this raceway, and also the thermochemical performance inside of the raceway, is very important for the entire furnace operation. And experimentally, it's not possible to access inside the furnace when operating because of the hash condition with high temperature around 200 degrees C and high temperature around 4 bar. That's why our project aims to use this CFD-DEM numerical framework to better understand the raceway formation and the chemistry performance inside. This is the domain of the raceway model. Due to the computational power, we limited our simulation to only a slice of this furnace, and with only one single nozzle. The dimensions around 3 meter high and 2 meter wide, and also around almost 1 meter in depth. And this is a 3D visualization of this domain. And if I zoom in the injection area, you can see that again, we apply a mesh refinement for the nearby the injection lens. So this outer ring is the hot air lens, and this inside the cylinder is the injection of the pulverized core. And for boundary conditions, we have indeed the hot air is injected from the nozzle at around 1000 degrees C at a high speed is about 200 meters per second. So which indicates that we need to really resolve the flow because of the turbulence. That's why we need very fine mesh in this area. And with this lens, we have injected the pulverized core, which is again polydisperse, but with an average diameter around 100 micron. This pulverized core undergoes devolatilization and char conversion. And the devolatilized matter then undergoes the chemical reactions, which is actually solved by the FGM method, which I talked earlier. And the coke particles, they are much larger. They are around 3 centimeters, and they undergoes the same conversion reactions as the char of the coke particles. Here is some qualitative results, which shows the evolution of the raceway. So in the very beginning, due to the expansion of the CO gas in this whole coke bed, then we have actually a growth of the raceway in such kind of balloon shape. And however, it very quickly this raceway contract to a smaller size and also become a stable form with a very elongated shape look like this. So really with very short time, it becomes stabilized. And of course, we are not satisfied with qualitative results. We want to quantify the size of the raceway. What we do is we remove the core particles, where then we identify the area with the void fraction around 0.7. So we identify this area, then we should be able to measure the height and length of this area. This is what we call physical raceway. Alternatively, we can also identify another type of area based on the oxygen concentration. So this is a typical oxygen area by oxygen concentration look like. And with this, we can also measure similarly the height and the length of this area. This is what we call chemical raceway. And the boundary of this chemical raceway is determined by around 5% of oxygen molar fractions. So you can see that the shape and size of this physical and chemical raceways, they are completely different. And actually, in most of the literature, it is reported with physical raceway. However, we think it's much more interesting to look at the chemical raceway, because where the oxygen located is actually should be supplied for the coal and the coke gasification, and thus to be able to see whether the combustion is efficient. And these two plots shows the raceway size, mainly by the blue color is the height and the black color is the length of the physical raceway, and left plot is at the blast speed 200 meters per second. Right plot is at blast speed 240 meters per second, and we have done different core injection rate, so from without core and also with around 0.2 kilogram per second, and scale it up. As you can see very quickly, at the higher blast speed, we have the raceway side, the physical raceway slightly larger than the lower blast speed. However, in both conditions, the raceway size does not change with the core injection rate, and this gave us a conclusion that actually the core combustion has almost no influence on the formation of the raceway, of the physical raceway, by the way. So the formation of the physical raceway is primarily determined by the momentum of the blast air only. So how about the chemical raceway? And with that, first you can see, again, this is the height and length of the chemical raceway. So you can see that it actually decreased with the injection of the injection rate of the core particles, because the more core you inject, they should be able to let's say consume more oxygen, and then you have less oxygen to enter the coke bed. That means the chemical raceway size might shrink. However, still it eventually will converge to a stable dimension. At a higher blast speed, again, the size of the chemical raceway is become slightly larger than at the lower blast speed, and similar change can be seen, that eventually indeed it will converge to a stable size. And why it converged, and then we can understand it from actually the snapshots of the oxygen concentration. So indeed, the color in the bulk indicated by the oxygen concentration, and here we again put back the core particles, which are colored by the velocity. As you can see, that the core jet is injected from this nozzle, and it actually enters in an area which is lack of oxygen. And why does this happen? Because along this jet, the particle quickly, let's say, release the volatile matter, and this volatile matter will consume the oxygen very quickly, and the particle does not go along with the gas. So that's why they enter in the area where there's no oxygen to consume. And most of the oxygen, you can see that by this yellow color, are concentrated at outside of the region of this volatile matter flame, and then they enter the coke bed. And if we increase the core particle injection rate, as you can see that, okay, it slightly changed. However, almost the same amount of oxygen enters the coke bed. So that's why even if you further increase the core injection speed, it will not influence the size of the chemical raceway anymore. Yeah, and actually for this work, I have no time to talk about all the interesting findings. We have much more interesting findings. And again, I refer to our publication, so you can, it's still under review. Hopefully it will quickly be published, and then you can find much more interesting findings regarding, for instance, the injection angle, etc., for the raceway formation. Yeah, by the way, this result, of course, this findings indicate that the mixture between the core particle and the oxygen or the air is very important. So we need to develop strategy to enhance this mixture. For instance, now we can also enhance enhance the turbulence level of the blast gas. That's a possibility. Yes, and then the final example I would like to talk about is a so-called direct iron reduction in a fluidized bed. This is actually a part of the process in a so-called iron fuel cycle. So iron fuel cycle is a concept for energy carrier of the renewable energy. And what is iron fuel? If you look at this sketch, actually we use, for instance, renewable energy generated hydrogen. This is a green hydrogen. We use it to reduce the iron oxide into iron. So that basically means we store this renewable energy in iron powder. So we use around micro-sized iron powder, and this iron powder or iron fuel can be stored and also transported into anywhere the energy is needed. And when we need to use the energy, we burn those iron powders and to release the heat to be able to power the plants and supply the transportation and also household. And the only products of this combustion is water and iron oxide. So it's very clean. And the iron oxide, we collect them, and again, we can reduce them back to iron to regenerate the fuel again. So this closes the cycle. And in this case, the advantage of this cycle is that it's completely carbon-free, and iron has a high energy density and also very safe to store and transport. Most importantly, it has very little energy loss over seasonal storage. But the crucial step to close this cycle is the regeneration of the iron fuels. That is what I'm going to talk about it. And in this case, we use fluidized bed to carry out this reduction process. And we start with experiment. And in this is the sketch of our lab experiment setups. It's a cylindrical fluidized bed. And as you can see, we are able to inject either pure nitrogen or hydrogen or combination of both. And we installed multiple thermocouples to measure the temperature at different locations. And during the experiment, we keep track of the bed pressure drop. And the first thing we did is to measure the minimum fluidization velocity, at different temperature. This is the result we plotted in this figure. So the blue symbols are the experiment result under pure hydrogen condition, and the red is under the pure nitrogen condition. So as you can see, that the minimum fluidization velocity decrease with increase in temperature first. This is basically due to the gas property changes as a function of temperature. However, above around 300 degrees C, that the UMF actually increased with temperature. And if we compare the experiment data with the Ergun equation, we see that a good match at lower temperatures. And however, there's difference between the experiment data and Ergun equation, which is represented by the dashed line, at higher temperatures. So this difference we found out can be corrected by incorporating a centering force term in the equation. And so that is basically indicated by these solid lines. That is the line we add into a centering force term in the Ergun equation. This force term is essentially a cohesion between particles when at high temperatures, when the particle becomes sticky and they start to center. This is the kind of movie that when the fluidization is in a good condition at a lower temperature, you can see that very good bubbling being formed. However, at high temperature, when the sticking is happening, then you can see that the particle really stuck together as a big clump, and the defluidization completely happened. And this is, of course, pose a technical challenge for the development of this reduction process. So that's why we would like to use the numerical modeling to better understand the centering behavior of the particles inside the fluidized bed. Yeah, for more details of the experiment, this experimental research, you can find out in these publications at a few. And of course, to be able to simulate the centering behavior of the RM powder in fluidized bed, we need to add the centering force. This is also called solid bridge force in the CFD-DEM framework. This expression of this force, it depends on the tensile strength of the neck. You can see that there are two particles contacting each other at high temperatures. They become soft, and the surface of the particle diffuse into each other, and they form a so-called solid bridge. And this is the what we call the neck of this bridge. And this tensile strength of the neck is actually a material property. So that's we can obtain easily. And then it also scale with the neck size, which is this X. This neck size actually is it depends on many parameters. Many involve temperature and the particle size, and also the contacting time. So these are the three important parameter determines determines the strength of the solid bridge force. And there is also a constant C. This C is determined by the surface structure of the particles. It's usually corresponding to the smoothness of the particles. If particles become rough and this C also increase, that means this solid bridge force also increase a bit. And again, to be able to simulate the experiment setup, we need to apply coarse-grained simulation. So this is how it looked like when you applied this coarse-graining factor. And like I said, with coarse-graining, we also need to properly scale this solid bridge force. I will not give much detail later. Again, I will give the publication. You can find more detail about the scaling of this solid bridge force. And quickly to show you the result, and these are the snapshot sequence of the volume, the void fractions at two temperatures. Left is 500 degrees C, right is 900 degrees C, and at the top is without centering force, at the bottom is with centering force. You can quickly scan that. You see that at the lower temperature, that both conditions, even with centering force involved, the fluidization is quite healthy. So there's the bubble being formed, so very good. And at higher temperature, around 900 degrees C, so you can see that the centering force really become very dominating, and you see that the big glob is being formed, and basically the fluidization become very poor, and then that of course poses the difficulty of the reactions. We further did different simulations with different value of this C constant. Like I said, from left to right, there's a constant increase because of the roughness of the particle surface increase. You can see that at 500 degrees C, again, the diffusion, the fluidization of these powders can still be go on even at a quite high constant C. However, at the high temperature around 900 degrees C, quickly defluidization happens, and only without the centering force, then the fluidization can still carry on. So these findings indicate that the design of this process is very sensitive to temperature. So we probably need to keep the temperature well below 500 degrees C to be able to have a healthy fluidization condition. And we also, of course, thought about how to how to break the agglomeration or centering of these powders. What we tried is with increasing of the superficial gas velocity. So this again is a snapshot from left to right is the increase of the gas velocity from 0.12 meter per second to around 2.53 times. As you can see that indeed the defluidization is prevented. However, you can still see this sometimes some big agglomerate being formed, and with the color indicates the velocity of the particle. So you can see that those particles really become very, let's say, very slow motion there. So overall, we see that there is a tendency to break the agglomerates with increasing gas velocity. However, still, we believe the temperature is the most crucial operation conditions. Like I said, for more details of this numerical study, you can check out the publication from New at FUE. I think that brings me to a summary of my talk. We have developed a numerical framework to tackle challenges in modeling large-scale reactive multiphase flows, especially containing polydisperse particles. This framework is built based on the discrete element simulations. We have this coarse graining approach to be able to tackle large-scale simulations. And we also incorporate the FGM method for complex gas reactions. And for polydisperse size particles, we have developed a particle size dependent smoothing scheme, which can really capture the dynamics and also the mass and heat transfer of polydisperse particles in the system. And I have shown that we used this framework for successful simulations in modeling flame of pulverized core combustion, and also the race with a modeling in blast furnace, as well as the direct iron reduction through the gas bed. This framework is also, of course, a very general framework, can be applied in many other type of applications. And so if you are interested, check out our publications for more details. For the future development, we will work on is to extend this framework with non-spherical particles and also target at three-phase flows, especially with liquid injections. So those are, again, different type of complexity that we will work on in the near future. And finally, I would like to thank all the hard work, especially on the top of this slide. These three are three PhD candidates who really did most of the work I presented today. They are Chicha Huang and Conrad Hessos and Xin Niu. I also would like to thank for the nice collaboration with my colleague here, Julia Filatello, Tess Homan, and Neil Steen, and Jeroen van Ooyen. Of course, this research cannot be done without the financial support, which I also accorded today here. And thanks everyone for listening to my talk, and I'm happy to take any questions.